Hey everyone, so here we'll be continuing with our that introduction to recursion, and this will be part 2 video. I hope you are coming from that part 1 video because I'll be using that like concept because I have explained recursion in like in deep how recursion works internally and how everything like, and we got to know that recursion is nothing. It is just the nesting of function calls. The function like one function is calling another function is calling another, so this nesting is very deep. All right, so but if you are good with if you are good with function, if you know how function works, recursion is nothing for you. All right, so let's see this one thing that we are having trouble. That let's say you are given this tree, and you wanted what, to calculate the sum of all the nodes, to give me sum of all the nodes. So what we saw earlier in this, in this problem, that in recursion, I won't repeat that, guys, how we went, like how we approach the recursion and why we approach the recursion, because I hope you will, you are getting, you are coming from that video. So see what we were doing, because we know the see, for this f1, how can it calculate, see how this f1, how can it calculate the sum of all the nodes? There are few ways. First, it can go for all the possibilities. The root, it will go to left, left, then right, and all this way it will travel to every node, and it can calculate the sum. All right, this was one of its way. But the combinations are endless. You don't know how many combinations you will get, root, left, root. So in that way, this f1 will say, well, this f1 is having figured that I won't do everything on my own. So, and then it said, it said that I will handle only root, I will handle only my root and these new copies of f1. It will say that, because see, the duty for these f1, I'll come back to it later. Wait, I'll come back to it later. Have patience, guys. So this f1 said, I will only handle my root node, my key, and I'll give this left subtree and this right subtree, I'll give its work to these new f1 copies, to these new function copies, which just actually same f1, but a copy of them. So what, now see, guys, I hope you have watched that video and you know that why we went for recursion like this, because you see that the main test case, it was a tree and the child are also trees. All right, and you have to calculate sum. So this f1, it was getting what, it was getting tree as an input, and it has to give sum, and these functions, they are also getting tree as an input and giving sum. So the duty of these functions are similar. That is why we said that these are just copy of each other. These functions are copy of each other. Otherwise, you remember we wrote earlier f1 calls f2, f3 and f4. But here we saw that why we went for recursion, because the childs, they are, the way they are solved, see, the way the parent is solved is same the way child would be solved. All right, so this is why we went for recursion. But if you know, guys, but if you saw that video, so if this function, let's say this was first node, it called two other functions. It distributed its work of left subtree and right subtree sum to two other functions. Now again, this function will distribute its work to two other functions. In this way, this is a recursive tree. This is a recursive tree, and it is like its depth can be huge. Now every time, see, guys, if you are a beginner, I would highly suggest that at least for one or two problems, try to solve, like try to draw this recursive tree and think in that recursive, like think in that way, the way we approach this. But I would highly suggest that after you are done with, like after you are confident that how recursion works, never go for that. So but we have to solve that problem recursively. Now if you are not going for that recursive state and all these things, how can you solve that? So people came with this 3 step induction based hypothesis. Now see, guys, what was the problem? The problem was, let's say you are having this parent, this main test case, you called the new f1s on a reduced test case. These f1s will these f1s will again call these new copies for their left and right subtrees. All right, so the only problem was you are going endlessly, like in the left subtree, right subtree, then for that left subtree you are again calling left subtree, right subtree. So you are having many states to consider. But what people came with this induction based hypothesis, it says that look for only one state, look for only one state. Now how we can do that? See, guys, this f1, because the implementation will be similar. So whatever implementation you write for this f1, because these f1s are same, it's just a copy of this f1. These f1s are just copy of this main f1, so the implementation is same. So what they came up with this, see, for this primary, this first f1 function, this f1 was calling where this f1 said, give I will uh, call new f1, I will call new f1, these new f1s, and on where I will call them on, let's say this f1, he called this f1, this guy, he called this guy on its left subtree. It said that give me sum of left subtree plus and one more plus, I'll write something here, plus he also said that I will also call a new f1 for my right subtree, all right, for my right subtree. And what I'll do when they will return something, when they'll return their answer, I will just add my roots key value. That's it. So this function's job is done. All right, this function's job is done. Now see guys, earlier what we did, now this f1 will again call these new f1s, this f1 will again call these new f1s. So this is the problem, that if you go on this recursive way of thinking, you will get stuck. So what they came up with, that you have to trust this f1. See, once you are at this f1, this primary f1, this main f1, you just have, when you call this two f1s, all right, you have to trust on these f1s, that they will do their work properly. That's it. This is a way you have to trust these f1s. Look, you can go to their to some new depths, that this f1 is calling this f1, but see, we know that there is nothing like trust and all. This is not a relationship, there's no trust issues. All right, we know that when we were solving the test cases, when we were solving these test cases, we know that we drew all the test states and everything, and we know that there was nothing like trust. Everything was working fine. But in real time, we will not be writing those new states all the time. All right, this is why you just have to trust on these f1s. So this is why you will not go to their depth. Just write this f1 and f1. All right, just write these f1s, because this f1 was relying on these two. This is what we call as hypothesis. So hypothesis is what, when you just write and when you distribute its duty, this function's duty, to other functions, you just trust them that they will do the work. You don't have to go to their depth. Now see, hypothesis will work fine, no problem. But see guys, for this f1, even if these new f1s return their answer, left subtree and right subtree sum properly, but there is one thing remaining for this f1. It distributed its left subtree and right subtree responsibility to these new f1 copies, but still it is remaining. There is one more duty to be done by this f1, and that is to add a root value, add the root key value. All right, so this is what we call induction step. Now see, your hypothesis will work whatever way you think. See guys, we will go into one of the examples. Hypothesis is what you think that your f1, your new functions will work. The way you think they will work, they will always work. It's just you have to handle the induction. See guys, you could have done what, one minus, one multiply, one divide. So you could have used other operator as well, but they are not right. So it's just your induction step. See, after hypothesis state is done, it's just your induction step. If you handle that properly, the hypothesis and everything will fine. Your hypothesis and everything will work fine. All right, because see, let's say this f1, if you go into depth of this, generally you should not, but if you go into depth of this f1, if you see this f1, again this f1 will call for this left subtree and right subtree. So it has to rely on it. It will say that I trust you guys, just give me your answer whatever you get, and I'll add 2 to it. Now see, if you have not done addition, if you have done multiplication, let's say for by some error you did multiplication, now you know that this f1 can't be trusted. Why? Because it has not added 2, it has multiplied 2. So this is what, but if it has an addition, this f1 was trustable. So this is what I'm saying guys. See, at hypothesis, whatever you think, it will work fine. Whatever you trusted, they will work absolutely perfect. but it's just an induction step. You have to handle that properly. You did addition, right? You did addition. You can go for subtraction and multiplication, but if you go for subtraction and multiplication, it is not right. Then this trust issue arise. All right, so hypothesis, you can think in any way. It's just you have to handle induction. So you did this hypothesis and induction part. For this step, you will not go to its further child. Now there was one more thing. I hope you guys remember that there was one more thing. And what was that? Base condition. What I mean by base, let me write here. I will just erase or get some space. So see, after now, see here guys. So this main subtree, what was the nature of this problem, how we were solving this main tree? It called, like it shared its responsibility to other f1s, in a way that those new f1s, they got lesser test case, a smaller size test case. Now these test, if you see, so the test case size was reduced. So initially, if let's say this was the length, now this will be the length, then this will be the length, then this will be, finally there was you were getting, you reached at the end. See, this was the entire test case, you reached the end. Now if you again keep on reducing, see what were you doing? You were reducing, you were reducing, you were calling at every step, you were calling node left, node right, node left, node right. But let's say when you are at 8, you called node left, node right. So node left, there is nothing, so we say it is null. It is null. All right, so node right, it is also null. Now when you reach to null, it has nothing, it has nothing. So this is the last valid test case, null. This is the last valid test case, because see, at this test case 8, you are doing what? Nodes key value, you are getting nodes key value. But if let's say when you called for 8 left and 8 right, it was null. It won't have any key, because see, if it is it is simply like 8, it is not having anything in its left, anything in its right. So if you call node key value, if you want what key value for this null, there is no key value, so it will produce you error. So I will say that this is the final. So when you reach at null, you have to stop. You cannot calculate key value, because null does not have any key. Null means there is no node. When there is no node, how can you calculate key value? Does it make sense, guys? When there is no node, how can you calculate key value? So this is why we have to stop at some point. See, base condition is used for two purpose. First, you have, because if you go on and call that recursive state endlessly, so f1 will call, f1 will call, f1 will call this f1, f1 will call this f1. So in this way, this it will go on call and endlessly. So to stop at some point, you will have to like you will have. And see guys, first of all, when I say stop, what I mean by this f1 has to return this f1, because if it stays in this stack. So this was your primary f1, this was your main f1. All right, this was your main f1. This f1 called this f1, then this f1, then this f1. You again have to return to this f1. Now this is a stack, this is a memory stack, or call, or call stack. So only when this f1 is removed, this f1, then you will go to this f1. Now how will they remove? When their job is done. See, when this f1 will remove, when it's above f1, its duty is done, it has returned something, it has returned its execution to this. So which means we have to return, which means you have to execute a base condition. Otherwise, if you keep on calling, this stack will keep on filling, and it will not stop anywhere until the overflow condition reaches. So base condition is first for that. And second, you saw that if at null stage, if your node is having null, you cannot calculate key, because null, for a null node, which means there is no node actually, how can you get a key? So it will produce error. So base condition is just for this, first to stop that recursion, and second to handle handle error, like which we can say, because if you write nodes key value, it will get error. All right, at base condition, at that null. Now because we have to write that base condition as well. Now where should we write that? See, this was your induction and base, these things this was your induction hypothesis. So these two were your hypothesis, and this was induction. Now where should we write a base? Should we write base above them or below them? Let's first write below them. Now what was the base? Base was if node is equals to null, which means it is an empty, there is no node, there is no tree, I mean, you have to return 0. If there is no tree, the sum is 0. But let's see guys, If you write the base condition at the bottom after your induction hypothesis, if you call this base condition, now see, all the time you will call f1. Now when this f1 is called, every f1 will encounter this f1, this base condition will never meet. See guys, consider a scenario when every time you are calling f1, see, at some stage you called f1, right? You called f1, when this f1 is called again, because it is a function call, it will again call f1, it will never reach this base. If you write base at the bottom, it will never reach at this base because of this f1. So you have to write where? You have to write at the top. The base condition should be written at the top. Now what I mean, see guys, this, it will be clear for you. This f1 function, if let's say this thing, if you don't write base condition here, if you write base condition here, let's say you write this here. So see, this f1, when this f1 called this f1, again the same similar scenario. Now this f1 will again call this f1, this f1 will again call this f1, and if there is no base condition that it can hit, because you removed base from top, you added base at the bottom, so the base condition will never meet. It will always be f1. So the thumb rule is you have to write base condition at the top, because you have to make sure that like someone should encounter this base condition, only when then it will return. All right, so base condition should be at top. So what you got, first you have to write base, then induction hypothesis. All right, and hypothesis you can think in any way that your function will work. It's just you have to handle induction properly. All right, you have to handle induction properly. So this is one of the ways to solve recursive problems. Now let's see guys, let us use this base and induction and hypothesis thing, and let's try to solve a problem. All right, let's try to solve a problem. So the problem is you have to calculate the sum of this array. So one way is obviously to go for loop for I assign 0. We already know this already. All right, so one way is to go for loop. Now as I can say, see, this is how you have to think. See guys, if you write a function, let's say f1, what this f1 does, this f1 will give you some of this array. All right, this array. Now if I say that I will be having this 1, because this is my first element, I will be having 1 plus, give me some of this 2 3 4 5. Now see guys, what f1 was doing, f1 was just f1 was getting an array as an input, and it was giving you out some it was giving you the sum. Now see guys, again when you are having this 1 plus, now what is this? This is again an array. So and what you want, sum for this, so you can again reuse this f1. So this is how you can think of recursive solution. So here, by seeing test case, you know that this test case is also of recursive nature. All right, so let's see guys, we won't go for that recursive state and draw everything. We will use that IBH technique. All right, let's see. So first thing, we have to encounter base. Now see, encountering base, you will only think when you know what is your hypothesis condition. Now see, what I'll say, I will start from first index, which means 0th index, and I'll go to end, which means your last index, which is, let's say, 4. All right, so 4, I'll start from 0th index. All right, 0th index. So what will be your base? Because you will go in right, what will be your base right now? So your base, let's say till this point you are okay, when you're 5. After this 4th index, it is 5th index. So when you encounter 5th index, because in array there is no 5th index right now, so you have to return 0, because when you encounter 5th index, you cannot calculate its sum. You have to return 0. All right, so at base condition, see, I'll write a function fun. What it will handle, it will, let's say, your current index, whatever you are, let's say int of what we can say current index, comma, it will get to the length. Here the length is 5, which means the final index plus 1 length, and an array int arr. All right, now see, what is current index? So this main function, this entire function, initially the current index is 0. Now see, if we know we have to write the base first, if your current index, this curr is equals to n, which means you crossed your last index. Now you cannot calculate. See guys, if you calculate for this index value, there is no value. There is no value because array is up to this index only. So it will throw error out of bounds. It will throw error. So you cannot. So this is why you have to write base condition first. That if you reach at this index, you just have to return 0. All right, you have to just return 0. Now see, this was your base condition. Base condition is done. Now let's see what hypothesis is. So hypothesis will be what? You will call function fun for, let's say if you're at 0th index, you will say what? I will have my 0 index, no problem. I will have this value which is 1. Just call for this particular array. Call for this particular array. So function, I will call function current plus 1 comma n, because these things will come, they will be constant. That's it. So this is a hypothesis. All right, this is hypothesis. You will trust that, yeah, it will return properly. Now what you have to do, because this function, what was its duty? It has to return what? It has to return what? The sum of this array. So you got that. You will get the sum of this array. You will get sum of this array. Just you have to add what? ARR of current. ARR of current value. That's it. So this is how you will write. You will use induction base and hypothesis thing. All right. So base you have to write always at the top. Then, and while writing base, you have to think. While writing base, you have to think that what was your hypothesis and how was your test case being reduced. Now see guys, I will write one more solution for this. I will write one more solution for the same array, but with a different hypothesis. Right now, what I said, I will start from 0th index and go till last. But now what I'll say, see guys, earlier what we did, we started from 0th index and we went to last. But now, because see, solving a problem, we can have many solutions for that. We can have many approaches for that. All right. So that was one way, that going from starting index. Now what I can say, I will go from last index and reach till 0th index and then sum. So in hypothesis, how will I think? See guys, hypothesis means how you think and how you trust your functions. I will say that I will start from last index and till 0th index I'll calculate sum. So after 0, which is the index, it is -1. All right, if you go and subtract 4 minus 3, 4 minus 1, which is 3 minus 1, 2, so 0 minus 1. So when you reach -1, you will stop. All right, so let's see how will we write this right now. So let's say you are given a fun, you want to output, this is C++, C out fun. So I will start at final index. All right, final index means length, which is n minus 1 comma c, n minus 1 comma, and what is that? This is ARR. All right, this is ARR. So you will just do this. Now guys, be with me. Now it is integer function. Now see, what is n minus 1? It is a current index. It is a current index comma int ARR. All right, this is the array. This is your current index, integer current index. This is ARR. Now you know what is the base condition. If you start, now see this. See guys, this is the way of thinking. The different and different way of thinking. You can say that you started from final index. You will go in left. You will go in left. All right. While but when you are going in left, what was that condition where you have to stop? See, at -1 index you cannot calculate sum. You have no index, you have no value. So when, see guys, see here properly, if your current index is -1, which means this array is done. This array is done traversal. The traversal of this array is done. There is nothing remaining in this array. So you have to return 0. If there is no, like there are no elements, you have to return 0. All right. So this is your base condition right now. Okay. Now what was your hypothesis? At hypothetical level, what we are thinking, that so see this, I will get my sum for this value, for this current index. Just give me some of the left remaining ones. What do you mean? I will get for 4 index, give me the sum of the array till 3 index. All right, see, you wanted sum till 4 index initially, but what I say right now, on how I think, I will get the sum at 4 index. I'll know what 4 index value is. Just give me sum till 3 index right now, and I will add this 5. So hypothesis, what you will do now, fun current -1. So give me some of current -1 till current -1 index. till current minus 1 index, and this is ARR, and what this is hypothesis. And what I'll do, I will return, but when I will add this, what ARR of current, I will add current value, and then we'll return. Now see guys, this is also one way, and if you see, this is also another way. Here you saw that we were using 3 parameters, here we were using 2 parameters. The base condition is different, current is equals to n, the base condition is current equals to minus 1. Here in hypothesis we were doing current plus 1, here in hypothesis we were doing current minus 1. So see guys, hypothesis is a way you think, all right, the way you trust your function. There are many ways you can so here you saw that what, here you saw that we went from right to left. In this approach we went from right to left. What we said, that I will get my sum, I know this value, just give me some till my left index, give me some till my left index, which means, let's say if you want some from 0 to 4, I know 4th index, give me some till 0 to 3, I will add just 4. So this is one way of thinking. Here what was our way of thinking, that I wanted from 0 to 4. Let's say if I wanted some from 0 to 4, so what I'll say, I know my 0th index value, give me some from 1 index onward, which means 1 to 4. All right, so these are 2 ways of thinking, and there can be many ways. It's just guys, you have to make sure whatever base you write, base should be in accordance with what hypothetically you are thinking. All right, here you saw that base is current equals to n, here the base is current equals to minus 1, and it is the same problem. For same problem we are approaching in 2 different ways. All right, now see guys, this is pretty famous way of solving this recursion problem, IBH technique. There are a few more, and one of the very famous is choice diagram. All right, choice diagram. And this, while we will solve the problems, we will see that choice diagram. Initially we will start solving problems on IBH technique, then we will proceed with choice diagram. Choice diagrams means, see, if you remember this recursion thing, if you remember this recursion, before recursion, why we went for recursion earlier? Because if you want to calculate the sum of the nodes, you have to go through all these combinations. Root, left, right, all those things. And now what we know, and why we went for recursion, because recursion will go and see for every combination. And this is sometimes a problem. All right, and so choice, we will see that in problems, that recursion, what it does, it goes for every possible state. It checks for every possible state, it checks for every possible combination. And many a times you don't need this IBH technique directly, you can't figure it out IBH technique directly, you go for choice diagram, you directly choose. We will come back. See guys, I'm not confused right now, because I hope you got this idea of IBH. We will start the problems on IBH, and once we are confident in that, like 3 4 5 problems, then I'll go back and then I'll come on this choice thing. And it is not something new, it's not something which is totally different. A bit of difference between IBH, it will all see, choice diagrams, its parent is, let's say, IBH, it will follow the principles of IBH only, but I'll explain this after you are confident in IBH thing. All right, so I hope, to summarize this video, you will first write base condition, because you will not go in recursive state. For the parent problem, you will write the base condition, you will trust its childs, that's it. So base condition will be at first, will be at top, then induction and hypothesis. And hypothesis is a way of thinking, however you think, it's just how the way you write base and the way you handle induction, everything will be perfect. So do let me know in comments. See guys, this video, these videos might be a lengthier one in starting few videos, because I'm targeting the beginners who have problems in these sort of the topics. So do let me know in comments, like, do you like these videos or not?